Greetings. Welcome to Calculus of the PM. Section 4.3, derivatives of inverses. It says inverses of trig equations, but we're not going to just limit ourselves to just trig equations, okay? Actually, you'll find on the AP stuff, they do use inverses of trig equations from time to time, but I don't know, the textbook focuses too much on the formulas for the trig equations. You shouldn't need to memorize the inverse formulas for trig equations. More about that as we move in. But an inverse function itself, okay. We'll take a look here. And what do we have written down here in the notes? If the function f is differentiable at every point in an interval, so between 2 points, and the derivative is never 0 on that interval, then the function f has an inverse, and we'll call it -1, f -1, and it's differentiable at any point on that interval. Only on that interval. Now, what does this really mean then? This means that we can find the derivative of an inverse function as long as the derivative of the original one doesn't equal 0 on the interval. So there's no zeros on there. And there's a rule, but I don't want you guys to think of it as being memorized. I do hope you know what's in the box here. This you must know. Now, what does that mean? If you have a function and you put the inverse inside it, you just get the x back out of it. Have you thought about inverses much? Now, here's an inverse you're familiar with, because you've used this button, sine -1. Now, what does this mean? Yeah, the sine of what gives me 1/2, and I'm looking at this and I go 1, 2, radical 3, right? Which angle, we're going to talk radians, is it the pi thirds or is it the pi sixths? We'll try not to say 30 and 60 degrees. Which one gives me the sine that has an answer of 1/2? And it is? Shame on it. Pi sixths. It's okay, at least it said something. Sine is opposite over hypotenuse. SOHCAHTOA, SOHCAHTOOMI, whatever gimmick you guys use. Okay. But you know what I'm talking about. Now, I'm just saying this, okay. Now just think of it this way. What if I went backwards? I said, now, I'm just trying to like revive your memory here. What does this inverse mean? What if I said this? The sine of the sine inverse with, and I'm using this one because we've just thought about it. Should equal 1/2, but let's just think about this and work it through. Okay, so what is this inside part equal to? We just worked it out as pi sixths, okay. And the sine of pi sixths is equal to, we worked this out, 1/2. Now, do you guys see how an inverse undoes the original function? If you had a function, a simple function, like y is equal to x plus 2, what is the inverse function? So if you add 2 to anything, no. Just think of this. No. What, okay, I'm going to write it up. Okay. What if the function was, and then I don't want to take up too much space, so I'll erase this one out. If I said the original function is equal to x plus 2, do you guys remember how to find then? You know, x's and y's reverse each other, right? So you'd say, if you can't, I wanted to do one where you could just think it through, x minus 2, right? But if you're stumped and you want to do some swap in here, you go x is equal to y plus 2, and you'd solve for y, right? But you call y not, you wouldn't use y, you'd call it the inverse function, x minus 2. Now, I tried to give you something that was simple enough that you could say, well, if I add 2, the inverse operation is subtract, right? If you put the inverse function inside the original function, you're going to just get plain old x, right? That's what I really wanted you to see here. This I do want you to have memorized, and you guys have seen this. By definition, an inverse, if you put it inside the original function, just gives you back the inside, right? You come right back to where you started, okay? Now this, you should memorize. It's just the rule. What an inverse does is undoes the function. I'm not using math speak, but there. I think you understand what I mean. So, I think I'll run out of space if I keep this on. That's the only reason why I'm erasing. Now, what I'm saying is that the definition of an inverse, that's what's given in the box here. If you apply the chain rule to that equation and solve, you'll have the derivative of the inverse rather than memorize it. Now here's what I mean. So I'm going to write it out with color scheme. Outside function, and blank. Inside function. Okay, right? Now if I do the derivative of both sides, I'm going to use prime notation though, just it's more compact, right? We're doing the derivative with respect to x. Now we understand what this rule of inverses means. If whatever you put in, you get back out of it, right? So if I do the derivative, I have to do the derivative of the outside first, right? So what do I get? The derivative of the outer function, leave the inside alone. Okay, times the derivative of the inside function. I don't know what that is. Now it gets messy if you put f negative 1 prime. So I'm going to actually put a bracket around this. Because the prime, it's hard to distinguish between minus 1 and prime. So do you see what I did there? And that's only because it looks like 11 if you put it beside the inverse notation of negative 1. Now that's equal to 1, right? Because the derivative of x is 1. If you isolate for the derivative of the inverse, right? It's really 1 over, and then the rest of the expression. I'm going to see if I can fit that in here with my messy writing. Yeah. I'm just sort of scooching this up a little bit. There we go. Okay, now I've got space. Okay, so you can probably see that this is the derivative of the inverse. So that's the derivative notation, is equal to 1 over the derivative with the inverse untouched inside. Now, I have that right here in a circle, in an oval, actually. Ellipse, whatever. I didn't measure it exactly. So, what I'm saying is that if you truly understand what an inverse is, you can always work this formula out from first principles. By the way, this is the first section in your AP course that is exclusively non-regular calculus material. Okay, so this unit, you'll start to get something in your AP marks. You know what I mean, the calculus 30L mark, the local, as well. Incidentally, okay, so this is stuff that you wouldn't take in normal calculus. You will take it in university in Regina. It would be in your second course, some of the inverse stuff anyways. So you could memorize this formula, but I suggest that for this chapter, if you don't have it fresh in your head, work it out from first principles several times. You know what I mean? Like, oh, I've got an inverse problem. Write this down, come up with the formula. Now the reason being is that by the time May comes around, we're going to have a lot of formulas to memorize. I'd rather not memorize because I'm not good at, I do memory and stuff like this, but the fact is that you'll use it often enough that you'll know it. I wouldn't rely on your memory though, but I would rely on, I know what an inverse is, I can do the chain rule and apply it to this derivative and isolate for it and use this rule, okay? You can memorize it if you wish. That's one way of doing it, but you'll see what I mean. Okay. So let's try this. Now, you wouldn't actually use this method. You'll see when you use this method and so on. Now, if the function is square root of x minus 3, find the derivative of the inverse. We'll use the formula method. This seems kind of silly, though, right? On the side, though, I'm going to do something here. How do we find the inverse in this case? I swap the x and the y and then solve for y again, right? I'm calling f of x equivalent to y. X equals. So, right? Okay. And then we solve. Like you said, x squared. So, x squared plus 3 is equal to the, I'm going to call it the inverse. Okay. Does this work? Okay, and on the interval that is applicable, it does. What is the domain and range of this? Because this is important. Remember how it's on a given interval? The domain in this is starting at
more than equal to
3. Yeah. Greater than or equal to 3. And the range, what's the smallest value you can get out of a square root? 0. So it's 0 and up, right? So 0 is equal to or greater than. Oh, I said it backwards. I usually put the y first, that's why I'm getting mixed up. It doesn't matter, you can do it the other way around. Okay. Now, the reason why I'm saying this is that, you notice this function, you can use negatives in it and stuff like this, but it belongs, if it's an inverse truly of the other one, it'll only be half the parabola, okay? But we'll set that aside and leave it for that. Okay. Now, yeah, I don't even like this example that I'm saying, but whatever, anyways. We can do it this way. The formula method here. If we applied that formula, I don't like it. This is why I'm going to do this here. Let's just do the derivative of this expression here. Sure. Okay. F negative 1 of x, because this is pretty simple here. The derivative of this expression with respect to x is 2x, and that's it. Okay. The other way, it wouldn't make sense to do it the other way. We could, though, but then it involves a lot more work. But we'll get some chances to do this way. Don't you worry. We'll see. Okay. Some things to review. So I would just do it that way. Find the inverse if you can. If it's algebraic, you can usually find the inverse and do it that way. You'll see in charts and stuff like this, though, when you're going to play around with this. Okay. And a flip? Quick. Yep.
Is the x be outside or inside?
X be outside or inside? I'm not sure.
Find f of negative 1.
Oh!
Derivative x.
Yeah, this text uses that kind of notation. That's the same as this notation. Yeah, I got you. Yeah, it's not multiplying. Some review things. Now, I've mentioned this, the unit circle, stuff like this. I would not recommend that you memorize the unit circle, but you know how to use it. Because remember how I was saying, like, where do you get sine of 1/2 and all that stuff? Well, with pi 6, all you need to know is the sides of the 1, 2 radical 3 triangle, right? And just apply your positives and negatives. If you had something like 5/4, what would you do? Which triangle? Oh. 1, 1 radical 2, right? The 5/4 here. drawing it. Isn't this a multiple of 45 degrees, if in degrees speak, right? So, sure, but I'm going to go, this is -1 on this side, this is down -1, root 2. So if you need the sine or the cosine, you'd really imagine just this triangle from here, right? And if you wanted the sine, you'd say, well, opposite, -1 over root 2. If you wanted the tangent, you'd say -1 over -1, and so on, right? Okay. That's where the unit circle's handy. You only need to memorize two triangles, 1, 2, radical 3, and 1, 1, radical 2. And then just apply your positives and negatives appropriately. Now, the other things, you know how that all of these sides are related by the Pythagorean theorem, right? So that means Pythagorean theorem, well, cos squared plus y squared is equal to 1, right? That's a must. Cos squared of the angle. Oh, I was going to put y squared. Sine squared, okay. Now this is something you know, right? Now, do you guys remember if you have a unit circle? Now, I didn't actually draw this as a unit circle, right? Like, or I mean, when I put the sides in, as far as, I didn't pay attention to whether it was a radius of 1. It still works out the same, though, because it fits in there. Would actually be that's actually a triangle that's slightly larger than the unit circle. It would have been this big out from it. Actually, exactly this, you know, 1 out. Anyways. But thinking of this as the unit circle, cos squared plus, if this is my angle, oh, I didn't mean it like that. If this is my angle here, and I'm talking about this here, what is the cosine equivalent to? Because if this is 1, this is x, and this is y, is the cosine like the x or the y side? You guys remember this? No? No? Okay. I'll put this down first. I'll finish this statement here. And let's just see here. I'll do this one in green. Now, if this is truly a unit triangle here, I don't require that you memorize these triangles here as with 1 as the hypotenuse. But for this to work, the unit circle means that the radius is 1, right? Now, you've got an x coordinate, this length right here, and a y coordinate, right? Okay. Now, if this green is where my theta is, what would you say the cosine of theta is? Sure, it's adjacent over hypotenuse, which is x over 1. Do you guys remember this? Did you guys see it this way? What's that? Circoxertix is another way of reminding you. Yep. You're trying to say it politely, aren't you? Yeah. She was trying to be polite then. Okay. SYR. Sine is y over the radius. Yeah. Okay. That's another way of thinking of this. But do you guys see where the Pythagorean theorem identity comes from? The Pythagorean theorem. X squared plus y squared equals 1. Same thing, right? Okay. This comes in handy. As long as things are drawn to the x-axis, I didn't need to grab that right here, right? Any angle, you can describe an ordered pair, x comma y, as cosine comma sine of the angle that it makes. Okay. Also, graphs, you guys should just know these graphs. Now, the reason why I use it the most is just to remind myself. Okay, the sine function here. 1, 2, 3, 4, I think. 1, 2, 3. Yeah, this is my pi here. So, it goes up 1 and down 1, right? I didn't draw it that well, but it's good enough The reason why is I want you to come up with quick values. If I say, what's the sine of pi halves?
1.
You can think of this. If you want to sketch it quickly in the margin, go ahead. It's the top, it's 1. The sine of pi is 0. Because the other ones on the unit circle or whatever here, you can think of it that way too. But you don't get a triangle here for pi halves, do you? But since sine, yeah, okay, you get this. Since sine describes what the y is, it's a height of 1 on here, right? That's the same thing there too. Okay, in the cosine function, if I got 1 and -1 here, I'm going to plot ahead of time where I'm aiming for, and I'll see if I can sketch it fairly decent. Okay, and obviously this is pi halves. Okay. This shouldn't be news to you. This is all review. But I want you to have a little quick review. Now, the one that you might have seen before, but you haven't done a lot with, is the tangent function, right? You guys focused mainly on the graphs of sine and cosine. You might have seen the tangent function, but I don't think you ever applied. You didn't stretch it and translate it and stuff like that. Okay. So, what is the tangent of 0?
Sine of 0 is 0.
Yes, it is. Sine over cos, you could think of. Another way is thinking, on the unit circle, it is the slope of the line. It's 0 there. What is the slope at 90 degrees? Non-existent. Ding dong ding. Okay. The tangent at pi is 0.
So is the tangent the slope?
The tangent is the slope.
What was that other asymptote?
Asymptote? Yes, asymptote at 90 because, yeah. How about there? At 45 degrees, what's the tangent at pi quarters? 1. What would the tangent be at 3/4? -1. Those are your important points, okay? So let's just get this on here on this graph here. 0. How did I block this off? I have 1, 2, 3. I'll do it every 2, 3, 4. That's my asymptote I'm just putting there. Okay, let's think this through. Okay, so I've got 0, and I was counting at pi quarters, right? It'll be 1. Let's go with this as 1 every second. Okay? And then, sky high, right? So if this is pi quarters, the asymptote is at pi halves. So I'm going to go with this. What's that? Okay, then at -1, my 0 here I put here, but here, just make it like this. -1. Just thinking this through here. So this would be pi halves. I'm not marking on there, it gets too messy. 2 halves, 3 halves pi. Okay, and then a 0 here again.
So would that be an asymptote?
0 is not. Let's just take a look here. I'm just at plain old pi here.
I missed that.
Just from 1, yeah.
Okay, it's coming from the bottom.
Got it.
Okay. Now I didn't draw a full 2 pi on here. I didn't leave enough space. But you can see it just goes on forever with this repeating pattern. Okay. Now, you're not as familiar with this, and you're not going to have to come up with this graph too much or anything like this, but you should be aware of it. Okay? Now, you've worked this through a little bit. Is there any questions there? I'll just pause. So, I mentioned here, trig functions aren't one-to-one, meaning that they repeat values, y values are repeated. So you have to take, you can overcome this problem by restricting their domains, meaning that for the sine function, we'll go from, let's go negative pi halves to about pi halves. Now this is a rough sketch here. So, I know that this part goes like this. So this part's symmetrical. It's odd symmetry, actually. Right? So that part we can take the inverse of, okay? Now we could find the derivative of the inverse on that interval. This is sort of going back to that definition. Now let's just think about a few things here. We know how could I rewrite this? What does this mean? And I'll keep the x's and the y's with. Well, this means the sine of what is it? The sine, if I rewrote this, not exchanging anything like this, which one would be the angle? The y or the x in this case? The y. So this really means the sine of the y gives me an x. You guys follow me? That's the same thing? Like if I had 1/2 and I had pi sixths and so on, I could trade them around. We did that on the first page, right? So this is the same information but written in a way we can work with things, right? Now, if this is true, and from the first page, now I told you not to have it memorized, work it out from first principles, but right now we're going to use this as, we know that, I'm going to write this out here, the derivative of an inverse. I'm just putting this as an aside. 1 over f prime. Oh, I forgot to put this. And I wrote this part out wrong. I was saying f prime and I didn't write it down. Okay, we know this to be true, right? Now, we know what this means and all. Okay. Let's try this inverse then, the derivative of the inverse. So we know what this means here. I'm going to just toss, oh, I didn't realize I didn't have those attached. Okay, so this is, maybe I'm just trying to look for a place to put this here so it's not in the way. Sorry. Because I'm going to run out of space. Okay, so y is the inverse function, right? So in this case, the derivative of this inverse function. Okay, this is what we're talking about, right? Let's apply this formula to this. Is equal to 1 over cos, okay? And then the inverse function as is, right? Sine negative 1 over x. All I've done right now is this, right? I've just applied that rule. Oh, no, I got that. No, what am I missing? Or what do you think? Nothing? Okay. Now, we can make this a little easier. You said right off the bat that this is the y. Oh, I didn't mean that. Okay. Let's just call this y for a minute. Bear with me. Okay, this is equal to 1 over the cosine of y. Okay, that's what this derivative of the inverse is. Good question, yeah.
Isn't negative 1 units on the bottom?
I'm sorry, what's that? I'll just pause here too. But yeah, we know that the cos squared of y plus the sine squared of y is equal to 1. So wouldn't it make sense that the cos of y is equal to the root of sine squared y? Oh, other way around. I understand. 1 minus. Does that make sense? And if I sub that in? Okay. So then, the derivative of the inverse. So then back from here. So I'm going to use d by dx of the sine negative 1. The inverse is equal to, instead of 1 over cos y, 1 over what's that?
What was the use?
Okay, y is equal to the inverse, right? So, and I had y right here. So it's still y. So this is still y. Y is the letter that we're using. It means the angle. It's not like, it's like theta, basically, in that sense. Now, one last thing here then.
I couldn't you leave just like 1 over cos
1 over cos y? What?
y? Isn't it the same? 1 over
Well, you'll see something right away. Okay. Once we have, what is the sine of a function equal to the x coordinate or the y coordinate? It's equal to the x coordinate. Huh? You say it? Look at this. Remember how right off the bat I said, well, sine of y, what's that equal to? It's equal to the x.
1 minus x.
It's 1 minus x squared. So this is equal to, somehow, comes out to be 1 minus x squared. Well, there's the how. Now, you could memorize this. And you know what? It's not that useful. The odd time it'll save you a bit of time. You won't have to go through this whole thing, though, every time, and we'll practice something. No. You could do this for all of them pretty quickly. I have them, you can see I've written them out, like, I can rip these off real quickly in like 2 minutes maybe, max, if I just do them one by one, but I don't stop and talk about it. But it's the same process for all of them. But they are, where's the summary here? I have them all written down here. Now, instead of x's, we have u straight.